So, what are aerosols? NASA defines aerosols as minute particles suspended in the atmosphere. When these particles are sufficiently large, we notice their presence as they scatter and absorb sunlight. Their scattering of sunlight can reduce visibility in the sky and redden sunrises and sunsets. Why are sunsets so pretty and colorful? Thank aerosols. Although this doesn't mean that aerosols are always a good thing.
Aerosols play key roles in global climate change, but their exact role and the extent of their influence and impact remain complicated to this day. Global climate change itself is the very slow change in weather patterns over the entire world, as it changes not simply from day-to-day timescales, but timescales of many dozens of hundreds of thousands of years. Aerosols are a type of climate forcing, and climate forcings influence climate change. Aerosols in global climate change have both positive and negative forcing effects, and thus cause the overall planet to either gain or lose some of the energy it receives from the sun. This is important because if there is not a fine balance of energy going to the Earth, the energy differences could plunge the Earth into a runaway climate event. If there is too much energy being absorbed by the Earth, there is a runaway greenhouse effect. If there is too much energy leaving the Earth, there is a runaway snowball effect, which could launch the Earth into a harsh state in which all of the oceans are completely frozen from the surface all the way to the bottom of the Mariana Trench. This runaway greenhouse effect is what is predicted to have happened to our planetary neighbor, Venus. Its oceans are completely evaporated, and its surface is presently hotter than 400 degrees Celsius. Avoiding these absolutely catastrophic climate events would require us to understand the effects that aerosols have on climate forcings.
In order to do that, let's look at history first. There was a group called the IPCC, the International Panel on Climate Change. They were essentially a group of climate change science leaders appointed by the UN. These climate change leaders created a large report in 1996 about everything climate change related. And when they got to aerosols, they pretty much said, the more we know about aerosols, the more questions we have. We all absolutely need to do even more research. Fast forward to more current times. Let's take a look at a 2018 review on aerosols. It was written, "Till date, our understanding of different aerosol processes is not complete." So we could take away one of two things. One, what have scientists and researchers been doing for the past 20-something years? Or two, wow, this climate change business is deep. And aerosols are so complex. Is the government giving the scientists all they need to advance knowledge? Let's delve into this a little further. There's this project. It's called GASSP, the Global Aerosol Synthesis and Science Project. For this video, we're just gonna call this project GASP. GASP is an international group that is focused on increasing our understanding of aerosols. This can help me and you have a better understanding on how to save humans from potentially devastating effects of climate change. GASP made a beautiful, relatively easy to understand report in 2018 about everything aerosol related. One of their highlights is that for the last 20-something years, many techniques have been obtained to measure aerosols. We can measure an aerosol's size and composition and other properties using a variety of cool scientific instruments that have long names like scanning and differential mobility particle sizers, passive cavity aerosol spectrometers, aerodynamicity analyzers?
Aerodynamicity.
Kissity?
Cicity.
Cicity.
No, wait. Aerodynamicity
analyzers. Currently, we obtain a lot of aerosol data through remote sensors mounted on satellites, aircraft, ships, and ground stations that give us information on the microphysical and chemical properties, such as cloud layers and cloud dynamics, mixing state of aerosols, vertical distribution of aerosols, and large spatial coverage. It's obvious that scientists have helped us to understand much more about aerosols and how they work in specific environments under unique situations. This gives us a lot of hope and certainty that we can learn even more. Because you see, in order to better understand the effects aerosols have on climate change, we must figure out how aerosols work in environments that are not so specific, on a general, variable, global scale. Is this making your head hurt? Yeah, mine too. But no worries, we don't have to do the science ourselves. What we can do is support these scientists who are ultimately supporting us.
These scientists have put in a lot of work and have discovered many forms and categories of aerosols. Some examples are volcanic dust, desert dust, smoke, automobile emissions, factory emissions, and many more. Aerosols have similarities and differences to greenhouse gases. Greenhouse gases are gases such as carbon dioxide, methane, and water vapor that influence the way heat is trapped within the atmosphere. Aerosols are more complex. They have a cooling effect on Earth's atmosphere, except for soot, which come from fossil fuels. Aerosols are different than greenhouse gases since they are macroscopic and can be liquid or solid particles suspended in gas. Throughout Earth's history, aerosols have mostly come from volcanic eruptions. After a major volcanic eruption, such as the Mount Pinatubo eruption in 1993, the dominant aerosol layer is actually formed by sulfur dioxide gas, which is converted into droplets of sulfuric acid in the stratosphere. This aerosol layer in the stratosphere can take a week to several months to form after the eruption. Winds in the stratosphere spread the aerosols until they practically cover the globe. Once formed, these aerosols stay in the stratosphere for about 2 years. They reflect sunlight, reducing the amount of energy reaching the lower atmosphere and the Earth's surface, causing a cooling effect. Volcanic aerosols are an example of a direct effect on climate from aerosols, but aerosols can also affect Earth's climate indirectly by changing the properties of clouds. Aerosols are necessary for cloud formation, acting as a baseline to start the formation of cloud droplets. Higher aerosol concentrations in the atmosphere cause water in a cloud to spread over many more particles, each of which is correspondingly smaller. Smaller particles fall more slowly in the atmosphere, and this in turn decreases the amount of overall rainfall. This means that the changing of aerosols in the atmosphere can alter both the frequency of cloud occurrence as well as the thickness and rainfall amounts in certain areas on the planet. This indirect effect from aerosols can cause major problems, from shifting global rainfall, including drought, and negative impacts to agriculture around the world. Research has improved over the past decade when looking at the effects of aerosols on our planet, but certain components of aerosols' effects on cloud formation are still not fully understood. The inability to fully quantify these effects increases the uncertainty of aerosols' effects on clouds and what these effects could mean in the future.
In summary, we've talked about aerosols and their role as a climate forcing that influences global climate change. Unfortunately, despite thousands of scientific publications, we still sit at a shallow understanding of their net effect and influence on climate change. These scientific studies were conducted with some of the most state-of-the-art measurement techniques and devices, so it's definitely not human error that stifled our understanding. More so instead, our understandings are hindered by how young aerosol research is and their innate complexity and regional variability. One study in Italy may find results entirely different from China, Japan, or the US. Despite all of the complexities and uncertainties, we know of the different aerosols as well as how they are formed and how they evolve throughout time. We know for sure that aerosols impact climate as a forcing agent capable of both positive and negative forcings. We just don't know how strong these forcings are or how much they ultimately contribute toward climate change. For the future, we can be certain that we need to continue studying aerosols, and hopefully with more science, we can reach some massive breakthrough toward understanding how aerosols influence climate change, and thus avoid those apocalyptic runaway climate events. Anyways, thanks for watching, smash that like button, subscribe, and tell all your friends.